Now let's state Theorem 312 and prove it. Theorem 312 says that if f is a function from a set E into the reals, if it is one-to-one and continuous, and E is compact, then f inverse going from f of E back into E is continuous. Okay, well, we're eventually going to have to prove that a function is continuous, and we're going to use sequences for it. We're not going to use a delta epsilon proof. I started the proof, and I may be leaving out some of the justifications only because I've got quite a bit to write on this board. I'm probably going to fill it. Well, let's start with yn being a convergent sequence in f of E. And by the way, we know that there is a convergent sequence in it because f of E is the continuous image of a compact set. F of E is. F of E, therefore, is a compact set, so it's closed and bounded. Every bounded set has an accumulation point, and therefore, every bounded infinite set, therefore, there is a sequence, sequence yn that is convergent. Since f of E is compact, and I left off the reasoning behind that, because f is the continuous image of a compact set. And compact means it's closed. Since it's closed, the limit of that sequence exists and is contained in f of E. So we have a bunch of yns, a sequence, in f of E, and the sequence is convergent. It's going to converge to a number in f of E because f of E is closed. So we're going to define y0 to be that limit. Yn converges to y0, or y0. To prove that f is continuous, this should be, to prove that f inverse is continuous. This should be f inverse, and those should be f inverses as well. We only have to show that this sequence is convergent to f inverse of f naught. So we're taking a sequence in these numbers live in E, and they converge in E to f inverse of y naught, or y0. Well, let's denote xn equal to f inverse of yn. Another way of saying that would be that f of xn is equal to yn for all n's starting at 0, 0, 1, 2, 3, dot, dot, dot. And just, I put this in brackets, just this defines y naught to be f of x naught. Well, since E is bounded, it's bounded because it's a compact set, which means closed and bounded. Let the sequence xn, actually x in k, and maybe I'll indicate this is k equal 1 to infinity instead of the usual in 1 to infinity, be a convergent subsequence of xn's, of the sequence xn. And why are we able to do that? Because it's a bounded, it's a sequence that is bounded. Every infinite sequence has a convergent subsequence. Every bounded infinite sequence has a convergent subsequence. So we're letting x in k be a convergent subsequence from this. And we'll let z naught be the limit. The limit as k goes to infinity of x in x sub n k. So this converges to Z naught. Well, E closed implies that it contains all of its accumulation points, all of these limit points, so Z naught has to be in E. And I guess I can continue this. I'll say, comma, and F continuous at that point implies the following. The sequence F of this, F of x in K, converges to F of Z0. That's simply because F is continuous. So any convergent sequence or subsequence in the domain is going to converge to a number in the image. I guess I should have said this sequence xn is in the domain. F of xn is in the image. F of xn is going to converge to F of z naught because F is continuous. I'll go ahead and write theorem 3.1 is the justification for that. Well, that implies that y sub nk, which is equal to that, converges to F of z naught. But what do we have here? We know that yn converges to y naught. Writing really small there. Implies that if this is a convergent sequence, it converges to y naught. Any convergent not even have to say any convergent. Any and every subsequence will converge to y naught. So therefore, this y sub nk, the subsequence, also converges to y naught. Now remember, from above, these are equal. These two are equal. Since F is 1 to 1, F of z naught equals F of x naught implies that z naught is actually x naught. Just the definition of what it means for F to be a 1-to-1 function. So we're just about done. A couple sentences to clarify. Since an arbitrary, I'm going to abbreviate that ARB, subsequence of xn converges to z naught, which is the same as x naught, we see that xn converges to x naught by theorem 1.15. If an arbitrarily chosen subsequence of this converges to this, that means all subsequences will converge to that. It was chosen arbitrarily. If all arbitrary subsequences of a sequence converge to the same point by theorem 1.15, the sequence is convergent and converges, of course, to the same number. All right, I think one more long sentence and we're done. Since xn is equal to f inverse of yn. Now these are sequences, n equals 1 to infinity. I may have left them off on some of them. N equals 1 to infinity. And x naught is equal to f inverse of y naught. We see that f of x in inverse converges to f inverse of y naught. And therefore, what we're trying to prove, f inverse is continuous. And we just proved it's continuous at y naught. But that was chosen arbitrarily. Therefore, we've shown that it's continuous at every point in its domain, and therefore f inverse is a continuous function.